we're going to finish off this course now by, let's see, basically repeating the whole course in 2 hours or 3 hours. So the title is Electrodynamics in 2 hours. And the point is to repeat the key points of the whole course. So we'll see if I succeed in doing that in so short a time. First of all, I would like to remind you that all you need is, and it's not love, at least not on the exam, but rather it's that the divergence of D is equal to the free charge density. That's the first law of Maxwell. The B field has no divergence because we haven't seen any magnetic monopoles. The curl of E is equal to minus dt B. This was called Faraday's law, and this is what runs our electric motors, our rail guns, and whatever transformers, other gadgets in your home. And the curl of H, that says if you rotate a magnet you can generate electricity, J, electric current. And then there was a time derivative of D, which ensured the symmetry with this law, so we can have these propagating waves, that is light, which is, as you know, very convenient. Okay, we also need the Lorentz Force Law. And this is to be able to couple what happens in the electromagnetic domain with what happens in the mechanical domain. So if I shine light on something, I exert a force on it, and so on. And to calculate these things, we use the Lorentz Force Law. It's Q E plus V cross B. And finally, to make any sense of these equations, we need the constitutive relations for the material that we're discussing. And these are some sort of mathematical entity that connects D with E and B with H. In general, these can be very complicated. For example, someone has made artificial materials which have an internal structure. And this structure is so that both epsilon and mu is negative. And this, in fact, gives you a negative index of refraction. So you can construct some pretty crazy constitutive relations if you construct a material with odd properties. Okay, so the point of the D field was to automatically take care of polarization. Because we included that. Recall that D is equal to epsilon plus epsilon naught E plus P, the polarization. Also H equivalently takes care of the magnetization. Meaning, well, if you go back to the equations, you see that these are given just by the sources, meaning that you don't need to take care of to think about what material you're in when you're calculating them. And then afterwards, you can find out the E field and the B field from the constitutive relations. So if I were going to give a 5-minute repetition of the course, this would be it. And if I'm going to give you one advice for the exam, I would say that if you learn how to start from these and then figure out what you want, then you'll be on safe ground always, no matter what shows up on any exam, in principle at least. The mathematical calculations can be hard, but this is all the physics. Okay? So if you know this, then I think you can figure out anything. So if you're looking in the book and you're thinking, what the hell, what does this formula mean, where does it come from? Does he pull it out of a hat or his ass? Well, you go back here and you figure out how he got there. And then you'll figure out what assumptions did he make as well. And then you'll see why the formula breaks down in some special case. Okay, so that's That's the most important part. Now, let's move on to each part in detail. And first of all, I want to discuss electrostatics. And the approximation we make here is as follows. It is that all charges are at rest forever. And then if you know this assumption, you can just go to the Maxwell equation and figure out what are the equations of electrostatics. And the equations of electrostatics are then easy. If you look here, since they're at rest forever, there's no time derivative. Since they're at rest forever, there's no current. Since there's no current, there's no magnetic field. And since there's no magnetic field, there's no magnetic flux density. Hence, we have only two equations left. And those equations are that the curl of E is equal to 0, and also that the divergence of D is equal to the free charge density. Now, this equation here means that there's no curl in the E field, and a vector field without a curl we can write as a gradient of a scalar field, meaning that we can write the E field as follows. E is equal to minus gradient of V. And now since V is a scalar field, this implicitly means that, well, the curl of E is equal to 0 because the curl of a divergence is always 0. So I can just neglect this equation here. If I instead insert this here into this equation, then we see that the normal square of V is equal to minus rho over epsilon naught. This is the Poisson equation. As you can see, we started out with the 4 Maxwell equations. We stated our assumptions, and we found out a simplified equation for the special case at hand. So no need to go remembering all the formulas, because you can just find them from the Maxwell equations. And now this is an inhomogeneous partial differential equation, and it has the following solution. It's minus 1 over epsilon naught integral over g of r prime, where g is the Green's function of this operator here, and rho of r prime d3 r prime. And the boundary condition is, of course, that at infinity the potential is 0, because we recall that the Green's function is defined with an operator and a set of boundary conditions. And we'll just assume that at the edge of the universe there's no charge around, and so V is equal to 0 at infinity. And this means, let's see, yeah, and recall that the Green's function, we found it through blood and sweat and hard work to be equal to minus 1 over 4 pi r vector minus r vector prime. And to remind you of the standard coordinate system we use, we have the origin in some unspecified location. We have the sources here, rho. We integrate over all rho r prime, which point at various positions in the charge distribution, and we observe the field at point P, which is given by r vector. As you would expect, the only quantity to appear in the solution is the distance, or the difference of these vectors. So it's r minus r prime that occurs in the in the solution. It doesn't depend where I put the origin. That's to be expected. We also had some special cases for this rho. Which was the so-called source term in our inhomogeneous partial differential equation. And one of them is a point charge. And that we can write as rho of r prime is equal to q times delta of r prime minus r q, where the charge q is to be found at position rq. Okay? And if I insert this into the solution, then v is equal to q over 4 pi epsilon naught delta of r minus r, let's see, r prime minus rq times 1 over r minus r prime d3r prime. That's a lot of writing, but this delta function makes sure that this integral is really easy. It's simply, let's say, a sum over point charges. If you have several point charges, you just sum up additional delta function terms, and you get one from each delta function. So we end up with q over 4 pi epsilon naught r minus rq. And this here is the distance from the point where the charge is located to the point where we're observing the fields. So again, you don't need to remember these discrete formulas or the special case summation formulas over point charges. You just need to recall that, well, I can write it as delta function, and then the whole machinery is ready for you to use. If you have a line charge, you can do the same thing. Which is basically rho of r prime is equal to some q over some L. That is, you need to have some sort of charge per length times delta of, for example, x, delta of y. Now this is a line charge stretching out along the z-axis with, which is infinitely thin because of these delta functions, and it has some charge per length. Okay, and same if you have a surface charge, then you just put one delta function, which is transverse to that to the surface. Okay. Any questions? No. Okay. All right. Now in electrostatics, we also had some special techniques show up. Wrong lecture notes. Okay. So, special techniques. And in this context, I would remind you of the uniqueness theorem. And the uniqueness theorem basically says that if you have a boundary where you determine the potential, then V is determined. That's all you need to determine the potential V. Okay, and this means that any function V that satisfied the Laplacian of V is equal to rho over epsilon naught minus sign, and the boundary conditions, that is the correct solution. There's only one solution which does that, and that is the uniqueness theorem, in other words. It's actually a corollary of the uniqueness theorem, but it's an important one. And this means that if I can think of a function that so happens to match the boundary conditions, well then that is the solution, because there is no other solution. Okay? So if you can just pull out a solution out of a hat, or by divine inspiration, that solution is fine. You just need to check that it obeys the equation and the boundary conditions. And this is particularly useful in the method of images. And the method of images is basically that you have some real problem that you try to solve by thinking of an equivalent image problem. And by that I mean, if you have, let's say, the following case, where you have, well, the simplest case is having a metal, and say some point charges in this region here. So if I have Q1 and Q2, let's say, this is the real problem. And then the equivalent image problem is as follows. We have the, let's say, x and y axis. Draw those first, so x and y. So now let's say, since this is a metal, I can just ground it and say that V is equal to 0. And the metal stretches to infinity along x and y. Then the equivalent image problem is that you have, let's see, you have Q1 and Q2 here. To match the boundary condition here, we add 2 extra charges down here. So that's Q2 bar, that's an image charge, and Q1 as well, so Q1 bar. To match this boundary condition over here, well, then you need image charges over there. So Q1 tilde and Q2 tilde show up over there. Finally, because now the net charge is opposite of that we originally had, because these were opposite in sign of these guys, and then we kind of screwed up. When I try to satisfy both this boundary condition and this one, then those two screwed up the result, meaning that I will finally have 2 charges down here. So that's Q2 hat and Q1 hat, placed symmetrically, even though it doesn't appear so to you now. Now, since this is simply point charges in a vacuum, you just sum up the potential from each, and then you got your potential in this region up here. So you basically just keep the part of the solution which is in this quadrant here, in the first quadrant, and just reject all the other stuff, since we know that V is equal to 0 inside the metal. Okay, so that's an example of that. You can in fact use this in radiation as well. You just, or in if you have some stretch out charge distribution, because then you just do a multipole expansion, and then each multipole can have its image multipole. And if you have retardation effects, then you need to put retardation on these as well, so you'd have an extra path length. So it's not necessarily confined to simple electrostatics. It's a nice method. We have a standard mathematical method for solving the Poisson equation, or other partial differential equations, which is called separation of variables. And this is basically to say that the function we're seeking, in particular V, is a function simply of a product of function, each depending only on one variable. So let's see, in the Cartesian case, this simplifies to the following, that V is equal to some function large x of small x, large y of small y, large z of small z. So these are functions which depend only on one of each of the variables, x, y, and z, which show up in the Poisson equation. A concrete example of this is if you have, let's say, some cube. This is supposed to be a cube anyway, like this perhaps. So there you have a cube. For example, now I can say that the potential here on this top surface, V, that's equal to some V naught of, let's see, if I draw some axis, x, z perhaps, V naught of x, z. And the other surfaces, I say that V is equal to 0 on the other surfaces. So there's 5 surfaces where the field is 0, and there's one surface where you have some non-trivial potential, And we solved some examples on this form. Then you can simply solve this problem by separation of variables. Typically, if this function is not a sine or a cosine, you need to form it by adding up many solutions, because the Poisson equation is linear, meaning it follows the principle of superposition. So a sum of solutions is also a solution. And it's the boundary conditions that determine what the solution is. Okay? So again, you see that the boundary conditions are essential. The math is well known. The solutions are well known. What determines the solutions we get is the boundary condition. Okay? And also in a spherical system, that is, if you have some spherical symmetry, then you can write V as some function of the radius, some function of the angle theta, and some function of the angle phi. So if you recall, you have x, y, z. This is theta. This is phi. Sorry. This is phi. This is theta. And this is r right here. Okay, so if you have some system with a spherical symmetry, let's say some conducting sphere or something like that, then you can easily solve this, more easily solve this boundary condition problem by using separation of variables and the spherical coordinates. And I'm pretty sure you've done the same thing in quantum mechanics when you find the wave functions for an atom. Let's say a hydrogen atom, for example. Okay. The last, I think, the last special technique we have employed is the multipole expansion technique. And the idea is basically that if I have some rho which is of finite extent, and I want to know the field far away from that, then is there some approximation I can do? And the simple answer is yes. If you recall that V is equal to 1 over 4 pi epsilon naught integral rho of r prime r minus r prime d3 r prime, and the coordinate system is the same as we always use. Then we can multipole expand this denominator here, meaning that 1 over r minus r prime can be written as, let's see, 1 over r, the unprimed r, plus sum over r prime divided by r to the power n pn of cos theta. N went from 0 to infinity, and Pn, say of x, those are the Legendre polynomials. And theta, that's the angle between r and r prime. Okay, so the whole point of this expansion is, of course, that we try to see if just a few terms is enough to describe the potential far away from the source. That's the whole idea. If you need to keep a lot of terms, then either you're doing something wrong or you're too close to the source and the approximation breaks down. So this is nice if you want the potential far away from something. And as you recall from the radiation chapter, you can put retardation into this and use this in general time-dependent electrodynamics as well. Okay, any questions on electrostatics?
Maybe, I mean, we learned how to solve the Cartesian example, but in the spherical example, maybe we give the solution, or do we need to know how to derive it ourselves?
Well, what's going to be on the exam, I can't tell you because I haven't made the exam yet. But we did this for. We did an example of this, I believe, or at least I know there's an example in the book where you have some conducting, no, you have some dielectric sphere, I think, and you have some electric field. No, it's a conducting sphere, and then you get some charges here, right? And then you can write the solution here as Legendre polynomials. So it's basically it. Yeah. So you
expect us to be able to solve it, right?
The stuff in the book, yeah. Not the completely general case, because you can get arbitrarily complicated expressions, but since it's in the book, it's part of the course curriculum. Yeah. But sort of the level should be, let's say, what's in the book. Same with that. Okay. By the way, I think some of you left their book here. Yep. Okay. Anything else? Okay, fine. We move on to electric fields in matter. And the conclusion was that, well, if you're going to work with the electric field, then you get some polarization, which you don't know. And the polarization generates a new electric field, which generates more polarization. And it's sort of, you have to solve it self-consistently. Alternatively, and more clever, we introduce the electric displacement D, which is equal to epsilon naught E plus P. And this is the definition. It's not that D is equal to some epsilon R, epsilon naught E or something like that. This is the definition. Okay? And for some special cases, we could derive the explicit constitutive relation. And to just quickly discuss some examples. Well, some of these examples, we have the linear, isotropic, and homogeneous dielectric. And now I'm going to ask you to explain to me again what is linear. Someone explain that?
E is the first order.
Exactly. Isotropic. Exactly. Homogeneous. No one knows it. This is a bit disappointing. Yeah. It's the same everywhere. Okay? The material properties are the same everywhere. So linear means that we only go to first power in the electric field. Isotropic means that if I look in a different direction, I see the same material properties. And homogeneous is if I move around in the material, I'm going to see the same properties as well. This gives me the following simple constitutive relation, that a component of D is equal to some scalar epsilon times the same component of the electric field. This is a scalar, and it's equal to epsilon r, epsilon 0. Now, if we consider an anisotropic material, but it's still linear and homogeneous, then the constitutive relation can be written simply as di is equal to epsilon ij ej. And epsilon ij, that's a rank 2 or order 2 tensor. Yeah. So if you have, let's say, a different polarizability in this direction compared to this direction, then you need to have a tensor here to take account of that. Also, if you have a nonlinear anisotropic but homogeneous material. Then you can write the displacement field as a sum of terms. di is equal to epsilon I j e j. So that's this linear term. And then plus epsilon I j k e j e k, and so on. So you go to as high order as you need in order to capture the sort of the dominating behavior of the material. This is, by the way, not the Levi-Civita tensor, but rather the dielectric tensor of second order. Okay, but we didn't give a lot of examples on of these two, but this is, for example, used in circular polarizers, and you'll learn more about that in the optics course next year. And this is used in, for example, laser setups where you want to generate sums of frequencies, because then you can actually generate the sum of a frequency or a difference of frequency, and a lot of interesting effects if you have a nonlinear material. Okay, I think that's about it, what I'm going to say about electric fields in matter. So any questions on that? No? Right, then next topic is magnetostatics. And we basically did the same thing as in electrostatics, except now we assume that there are no charges and that the currents have been running forever and that the currents don't move in time or change in time in any way. And you have heard in previous courses about Ørsted and the Biot-Savart law, which gave rise to forces between conductors, so you know about that. We can also note that in this approximation, divergence of B is equal to 0 and curl of H is equal to J. Those are the two equations that matter. This means that you can write the B field as the curl of a vector field. Now this explicitly incorporates this, or perhaps implicitly incorporates this equation here, because the curl of a vector field does not have a divergence. So this means that I can reduce these two equations to just one equation. And A is what we call the vector potential. Now if we choose the Coulomb gauge, that the gradient of A, divergence of A is equal to 0, then A simply satisfies the vector Poisson equation. Now the square of A is equal to minus mu naught times J. This is an equation which component by component looks exactly as the Poisson equation for the scalar potential, meaning that I can use all the mechanics from there. I can use the solutions, I can use the approximation methods, I can use everything. And the solution is known because we know the Green's function. It's g of r prime. It's minus 1 over 4 pi r minus r prime, like that. Still assuming that A is 0 at infinity. And the solution, A of r, is simply equal to mu naught, and the integral over the Green's function times the sources. So g of r prime, j of r prime, d3 r prime. Same as for the scalar potential. Yeah. Also here we can have some special cases for the current distribution J. For example, a line current is of interest. This typically occurs in electric wiring like you have in your homes. And this you can write as J is equal to I naught delta of x delta of y, for example. So if I have a wire running in the z direction, then I should have a z hat as well, I guess. You see it's infinitely thin, and it runs a current I naught. So if I integrate over these delta functions, they simply return 1. So I multiply by the appropriate constant to get the special case. And surface currents, you introduce those in a similar fashion as we did for surface electric charge. You just put a delta function for the direction transverse to the plane, and you're good. And again, you just insert these delta function expressions into the integrals, and then you get to the so-called discrete case where you sum up contributions for point charges or line currents or whatever. I think we very quickly discuss magnetic fields in matter before we leave. So magnetic fields in matter. These are this is handled quite similarly to that of the electric fields, except that very few materials have very strong magnetic responses to an external magnetic field. We recall that we introduced the H. Again, the definition is 1 over mu naught B minus M. So this is the definition of H related to B. Nothing else. Okay, but now for magnetic fields, we typically had 3 different behaviors. And those were, first of all, diamagnetic. And for diamagnetic materials, we had that chi m in absolute value was less than or approximately 10 to minus 4. And chi m is in fact less than 0. So the material tries to create a magnetic field opposite to that of the external field, except it's not very successful because chi m is so small. And paramagnetic, basically chi m is still small, but it's positive this time. So it generates a magnetic field parallel to the external magnetic field. Okay, we can write H for a linear material as 1 plus chi m b. Here you see that when chi m is 10 to minus 3 or something like that, then its contribution is very small. So we can quite often neglect this effect in a lot of materials. So that's, this is typically okay for these 2 material types. But it's not okay for ferromagnets. And ferromagnetism is a highly nonlinear effect. It's a very strong effect. You can see that by plotting M, the magnetization, which, by the way, is given as, let's see, chi m h, if I'm not mistaken. So if I have some current running in a loop around some ferromagnet, so let's say I have a rod of iron. That's where the name ferromagnet comes from, by the way. You have some loop of wire running around here. Well then, when you plot the magnetization as a function of I, it is indeed not a function because it's multiply valued. So if you start out with 0 magnetization, ramp up the current, typically goes like this. You have some saturation effect where if you increase the current more, you get no more magnetization because all the little magnetic dipoles in the material are aligned. And but when I try to go back to 0 current, the material remembers that it was magnetized. Okay? You might have tried this at home, perhaps, I don't know. You can just take a nail and run a wire, put on a battery, run the current for a while, perhaps knock it on the head, in fact helps. Then you get some magnetization after you turn off the current. But I can, of course, remove the magnetization by running the current in the opposite direction. So this was a bit strange, this curve, but let's see. Well, something like that. But then we end up with magnetization in the other direction. So this forms a typical so-called hysteresis loop. And this area here is an energy loss. So this is what makes transformers lose most of their, this is the source of most of the energy loss in transformers, electric transformers. So I think that's it for today, and we finish off the discussion by all the time-dependent effects, which is the new stuff in this course, on Wednesday.